Hello friends, welcome to Pioneer of Success. We are starting a new course on comsol for beginners. We already have another course on this particular topic. However, we are coming up with a new course so that we can tell you more details about comsol multiphysics. This course is being done for the students, for the researchers who have just started their comsol simulations and struggling with various aspects of comsol multiphysics. We'll try to talk each and every thing of comsol multiphysics in detail so that it becomes helpful for researchers, for students, and for other technologists. So we start with the topic. The first lecture will cover about the COMSOL interface, what are the options available, what are the opportunities, and what are the applications we can target with COMSOL multiphysics. Before we start the first lecture, I would like to tell you that we have also created customized courses for researchers wherein we support a researcher to develop their research problem. If you want to avail this course, you can write to me in the email ID given in the description box. So let's go ahead with the first lecture. So as you open COMSOL Multiphysics, you will be getting a window like this. And here you have two options, the blank model and the model wizard. So initially we have to click on the model wizard. Once we click on model wizard, you will be getting this option. So those options are the coordinate systems, the coordinate system you want to go ahead with. So you have three-dimensional option. If you are trying to simulate a model, you are trying to simulate a case in 3 dimensions, then you need to choose 3 dimension. Similarly, you have 2D, 1D. I'll talk about 0D in a different video. I have also talked about 0D. I'll put that video in the description box so it becomes helpful. You have, apart from this 3D, 2D, 1D and 0D, you have 2D axisymmetric and 1D axisymmetric. So sometimes what happens when you do simulation, not only COMSOL simulations but also any CFD simulation, if you have a symmetry inside your solution space, then you can just take a particular section and simulate at that particular section, and then you can actually take a rotation, a revolution around it to get the visualization for a 3D, three-dimensional system. So those kind of simulations can be tackled using this 1D axisymmetric. So 1D axisymmetric means you are basically trying to simulate in 2D, but you have a plane of symmetry, you have a symmetry inside the solution space. So you are cutting a particular line and doing a simulation on that particular line, and then after the simulation you are just rotating it to get a two-dimensional view. In 2D axisymmetric, basically you are trying to do a 3D simulations, but you have a plane of symmetry, you have a symmetry in the solution space. So you take a particular plane and do your simulation on that plane, then take a revolution of say 360-degree to get information about 3 dimension. So we have also developed videos on this 2D axisymmetric and 1D axisymmetric. I'll put all the links in the description box so that when you are familiar with COMSOL, and then go to those videos and learn about them. So now once you are done, then you can choose any one of them. So initially, as we are learning, so we should start a system from say 1D. So we start with 1D. I click on 1D, and then say we'll start with a heat transfer problem. So there are multiple physics options available, like you have AC, DC, acoustics, chemical species transport, electrochemistry. So those are the modules of COMSOL multiphysics, and under this you have different options, like in AC/DC you have electric field currents, you have electromagnetic heating, you have electric circuits. And similarly, suppose in fluid flow, if you go through the fluid flow options, you can see in fluid flow you have multi-phase flow, you have single phase flow, you have shallow water equations. I'll be making few more videos on this particular topic, this is because this is very helpful. And you have say high Mach number flow, subsonic, supersonic flows. If you are trying to model a supersonic flow, then you have to go ahead with this high Mach number flow. Similarly, the people who are working with semiconductor, they have these modules, say semiconductor modules, Schrodinger's wave equations, and Schrodinger-Poisson wave equations. So people who are working in quantum mechanics, they know the importance of those equations, and you can actually model those quantum mechanical problem utilizing this module. You have structural mechanics module, very important for civil engineers, mechanical engineers, because if you are trying to simulate a beam, if you are trying to simulate a cantilever beam, or any the moment of a bridge you are trying to model, so those kind of stuff you have to do utilizing this structural module. You have mathematics module. Mathematics module is the heart of the thing. Like if you don't have anything, if you don't get any physics in any of the modules available in comsol, then you have the liberty to design your own module utilizing this mathematics module. So I have also created a series of videos on mathematical module. I'll put all the videos in the description box step by step so that you go through those videos and learn about the system. So to go ahead with, we go to the heat transfer module and we choose heat transfer in solids. There are multiple options: heat transfer in solids, heat transfer in fluids, and heat transfer in solids and fluids. So based on your physical problem, you will be choosing those boundaries, choosing those physics. Like today I am trying to model a simple 1D conduction problem, heat conduction problem. So heat conduction means when heat travels through a solid object, that is heat transfer in solid. So I'll be going ahead with heat transfer in solid. So I click on heat transfer in solids and then it will be added to the interface. So once you click on multiple physics, it will keep on adding in the bank, and then you have to go for the study. You click on the study. There are multiple study options. You have stationary study, you have the time dependent or transient studies. Say for the time being, today we are trying to solve a problem of unsteady heat conduction problem. So what we need to do is we need to go ahead with the time dependent option, which is the transient physics option. So I click here and I can double click here. If I double click, then it will be added in the physics interface. So we have taken heat transfer in solid with a transient option. So once you click on done, you will be getting this particular page, and that has different subsections. The left hand side you have the model builder section, and in the middle you have settings window, and here you have the graphics window. So comsol is a GUI, that is the graphical user interface with software. So whatever you simulate, it generates data files or the solution files, and you can actually plot those solution files real time, and you can see your things here. Now this is a default window, and we have actually set the default window. If you change this window, you have options of reset desktop. If you go here, you can see there are regular screen layout, widescreen layouts, and if I click say regular screen layout, it will be looking like this. I don't prefer to work in this particular window because I can't see the setting windows, the model builder windows properly, so I don't like this particular setup. So what I do is I always go to widescreen layout because it is very helpful to look at the model builder side, the setting side, and also the GUI side. Now if you look at the above options, you can see there are multiple options like home, like every software has, like definitions, geometry. You can understand from the name itself, the option geometry would obviously be useful for creating your solution space. You have materials, that means a comsol has a material library. If you are working with say a simulation of heat flow through copper, so you have to choose a material. But why we are choosing the material? Because when we solve a particular differential equations, then those differential equations come along with different physical parameters, and those physical parameters are actually dependent on the materials of choice. So you need to choose a material so that you can define the appropriate parameters that is pertinent to that particular material. And you have physics options, so we have already added those physics. So what happens, suppose you have taken the heat transfer physics from the starting window, but you forgot to take, say, you also have the laminar flow fluid flow module. Then what you can do, you can go to the physics, you have add physics option, you can click here and you can add physics separately. I'll be talking about all those things one by one, but today I'll just be briefing about the options. So you have mesh. So mesh is the heart of any numerical simulation. So what you basically do is you have a solution space, you divide that solution space into multiple grids, and the equations, that means the differential equations, you first discretize, and those discretized equation generate a set of algebraic equations, and you have to solve those algebraic equations at multiple grid points, and meshing provide you those multiple grid points. There are different kind of meshes in CFD. You might have learned about structured grid, unstructured grid. So herein we can actually put multiple grid options that will actually cover your unstructured and structured grids. You have option for study, like the way we have chosen time dependent options. You can have the liberty to put multiple studies and do separate simulations for multiple study options. Suppose what do I mean with multiple studies? Suppose you are trying to see how heat transfer is taking place in a transient manner. That means in one study you want to know about the transient or unsteady heat transfer. On the other study you want to know the steady state heat transfer. So you can choose a study that is transient, that is time dependent, and you can do your simulation. You can choose another study which would be stationary, and you can actually use that for the steady state simulation. So but today we'll be only simulating with transient heat transfer conduction equation. Now I have talked about those things, and yeah, results is for once you do your simulation, you'll be generating data files, and you can plot those data files and you can see the results in a graphics window. So that is why you have multiple options. You can do plotting, several kinds of plots, contour plots. You can do 2D line graph, 3D line graph. What are those things? I'll be coming each and every aspect in detail in this entire series. So do watch the entire series. Now I come to the model builder window. You can see in the model builder window I should initially look for, say, initially look at the parameters. So the parameters is, you can define your simulation parameters and you can enlist one by one here, so that later on you can use those parameters directly. Like you have a parameters of viscosity, and viscosity is 0.01 units, say, and then you can actually call this parameter, say, mu, in your simulation. You don't need to define every time 0.01. So that is the purpose, like the way we do in any coding, like you are doing a code in MATLAB or Python. So we do enlisting our parameters. The same thing is here. And then you have the option definition. I'll talk more about it in the upcoming videos. Now I come to the geometry option. If you go to the geometry, you can see in the setting window you have the units option. Whether you are trying to choose in meter, you have, say, micrometer, millimeter, centimeter, inches, and multiple options of length scales. So say for the time for the heat conduction, we go ahead with the centimeter options, because maybe you will be taking a rod of centimeter, a few centimeters of length and few centimeters of diameter. As it is 1D, there will be no diameter, there will be only length, because it's a single coordinate system. Now you have to right click on geometry, then you will be getting multiple options. In 2D I only get point and interval options because it's 2D. It's 1D. In 2D you'll be getting multiple planar options like circle, like rectangle, like square, or other polygons. So I'll be talking about those in detail. I have also created an entire playlist on geometry. I'll put that also in the description box, and if you go through the geometry videos, then you learn more about geometry. So this particular series is being created, and we are creating branches by putting description links in the description box. So if you follow those videos as I direct, then you will be learning every aspect of COMSOL multiphysics. So without further delay, we click on the interval option. Say I want to have a solution space of say 10 centimeter length, so I put 10 centimeter and click on build selected. So I get an option of a line of 10 centimeter distance. Say this is 0 and this is 10 centimeter. Now this would be my solution space. Suppose I will be putting a high temperature at the left corner and the right corner will be kept at a room temperature, and over a period of time how temperature changes at different points of the line, that we will be studying, and that is the ultimate option. Suppose now we need to know about the materials. So we have defined our solution space, that is one line, and we need to define what is there in that particular line. Suppose this is a copper wire, so we have to tell that we have to tell COMSOL that put copper in this line. So for that what we do is we right click on materials, we click on add materials from library. One window will be opened up here, and then we write say copper and click on search, or you can enter also. I write copper and pressed enter, or you can put search option also. So there are multiple copper options, and you have to learn about this COMSOL library. They have their, they have a user guide where they talk about everything they have in COMSOL. So I'll put the link of the COMSOL user guide in the description box so that you can have a look into it. Initially we'll be randomly going ahead with a copper. Suppose this one solid copper, say this one we choose. I can close this window, and yeah, so when you choose the material, you'll see if it is showing in blue, that means the material is selected in this solution space. If you don't want that material in that solution space, then you can again hover here and click, then it will be deselected, and you can see one error message is showing that is selection is empty. That means you have chosen copper but you have not defined where your copper is situated, and that is why this error message is being shown. Now if I select it here, you will see that error message is vanished, because now it understands, okay, I have chosen copper and here is the copper material. Now we go to the heart of the story, that is the physics, the heat transfer. So whenever you go to the physics, you should initially look for the equation you are solving. So in the setting window, you'll have access to the equations. So this is the heat transfer equation. Actually this is a long equation, but all the terms will be basically, most of the terms, not all the terms, most of the terms will basically become zero, and that's why we'll not be using those. Like we have chosen heat transfer in solid, so unsteady, the first term is the unsteady term, we'll keep it, and the second term is the convective term. We don't have any convection here, so this would be 0. This is the diffusive term. You can see it comes from the Fourier's law of heat conduction. I have created another playlist on Fourier series heat transfer. I'll put the link in the description box so that you can have access to the Fourier heat transfer videos. So we'll be basically taking these two modules, these two terms, so that we can have solution for the heat conduction, and all other terms will be basically 0. Okay, so now what I do is I right click here and I choose one boundary condition. So your equation you have taken, but when you solve a differential equation, you need to define your equation, you need to define your initial condition, and you need to define your boundary conditions. So the boundary, to define the boundary condition in every physics of COMSOL, if you right click there, you'll be getting multiple nodes. They call it nodes. Now I click on the temperature node. Again, you see when you choose, it shows selection is empty. That means it is looking for some place where you fit in. So we click here. So in the left hand side, say I define a temperature. Suppose I define some temperature 500 Kelvin. Now I was talking about parameter, how you can use the parameter. Suppose I say define T left, TL, or T capital L, say this is 500 Kelvin. You can define it here and then you can call it. So instead of 500, I can directly write TL. So that is the usage of parameter. I hope you understood what is the usage of parameter. Now on the other side, I want to keep room temperature. So I again right click on heat transfer module, choose another temperature node and I click here and keep it at room temperature, suppose 293 Kelvin. So this is okay, by default it is chosen. Now this is the initial values. So say at initially all the points were kept at room temperature only. So I keep it as a default option, but you can change this initial temperature. Now what I do is, so everything is defined. This is a second order differential equation. So you need two boundary conditions. I have defined temperature 1 and temperature 2. That means both the boundary conditions are defined. Now I go to the option mesh. Again I am telling why the meshing is required, because it's a numerical simulation. It has to discretize the differential equation. It has to convert the differential equation into set of algebraic equations, and then you have to, it has to solve those algebraic equation at those grid points. So meshing will create that grid. So there is an option of default meshing. If you just click on build all, you will create a mesh. You can see we can do a user control, you can do a physics control mesh. It's normal, we can go for finer, extra fine. Okay, we can see because it's a 1D system, but meshing is created. Now you have to go to the time dependent. There is an option of time range 0, 0.11. It basically means it starts from 0 time, it goes up to 1 time, and 0.1 means in each 0.1 second time it will store your data. So it is basically solving, but it will not store data at every point. You have to command on where exactly you want to save your data. So it will start at 0, it will save the data, it will go to 0.1 second and it will solve for it, it will save the data, again it will save the data when 0.2 second comes. Okay, so this way it will be going. So now I click on compute option. I hope this simulation will run. Yeah, it has started running the simulation. It will take a few seconds. Yeah, this is done and you can see how the temperature is changing with time. So this is how I want to see what was the temperature initially. This was the temperature initially, it was kept at room temperature 293 or something like that. Then when I go from list option at 0.1, if you see, this is how the temperature is varying. At 0.2, this is the temperature. At 0.3, this is the temperature. If you plot 2 3 at a time, say 0.3, 0.4 and 0.5, you see this way the temperature distribution is varying. And if I plot everything together as it was earlier, you see it has almost reached the steady state. Steady state means the temperature distribution will no longer change, but still we can see there are some gap between these two lines. So what we can do is we can run the simulation for a longer duration, for say 5 seconds, and we record the data at every 4.4 second interval. Again we click on compute. So it has started simulating again. Now I plot all the times and you see still it has not reached the steady state. So let's run the simulation for say 50 seconds and store data at each 1 second. Again I run the simulation. So you can see that it's not like we will know everything before running the simulation. Once we run the simulation, we analyze the data, then we understand about the system better, and that's why I am changing the time scale, because from the simulation I am having an idea of the time scales. Like this one, yeah, now you can see it has almost reached the steady state. If you zoom here, You can see now the temperature is not changing much with respect to time. So it has almost reached steady state. So you can say like at some time here, like say if I show you 40 to 50, say 32 to 50 second, if I plot, you can see the difference is very minimal. So you can say like at 30 second it has almost reached steady state. So there is no unique time in mathematical language. When I say it reaches steady state 30 seconds, that means it almost reaches steady state. You can't say like at specific 30 second it has reached the steady state, but I can see after 30 seconds the change of temperature is very minimal. So we can consider that it has reached the steady state. So today I stop here. This was the first video. I think that this video was interactive and you learned many things from this video. We'll keep on progressing with this series and I hope I can be able to help you. If my videos are helping you, do like, subscribe to our channel and please share the videos with your peers. Thank you.